Okay, so thanks to Simon for organizing these Haskell meetups, and also to Martin, who doesn't seem to be here today.
Yeah, he excuses himself.
It's always great to have him, and I've only joined very recently, but I'm very happy to come every time. And thanks for giving me the opportunity to talk here today. I should first introduce myself. My name is Herrmann. I'm a PhD student in computational physics in the University of Fribourg. And before that, I studied physics here at ETH Zurich for the bachelor's and master's. And besides that, I'm also very interested in Haskell in my private time, and have recently become interested in programming languages and compilers. And today I want to present to you what I've learned in the past, or some of the things I've learned recently. This talk is also largely motivated by a presentation that Stephen Deal recently gave in Berlin and Paris. And if you haven't seen that, I recommend to watch it. The link is in the end of the slides. I'm going to be using some of his code, otherwise I'm in no way affiliated, so if I'm doing anything wrong, that's all on me. Yes, to kind of manage expectations, I'm not an expert in this. I'm interested in this, and I thought it would be good to share these things with you. Also as a learning experience for myself, so if you see me doing anything that you think is wrong, please let me know. So I'm going to talk about compiling a simple functional language in LLVM and Haskell. You can find all the code here in this GitHub repo. It's currently set up to work with Nix shell. I'm afraid I didn't have time to set it up with Stack, but if anyone wants to send a pull request for that, that would be very welcome. So let's jump right in. What is LLVM? It's a compiler toolchain for generating native code for multiple different targets, like x86, 64-bit, ARM, and many more. It has many features, including target-independent optimizer, so you can benefit from lots of work from many different people. On the optimizing side, it compiles to native code and can also do this just in time. It comes with an abstract assembly language, and that one features infinitely many virtual registers, so you do not need to take care of any register allocation yourself. And the language is using single static assignment form. We'll see later how that works, but it actually turns out to be a very good fit for what we're doing today. Some of the things that use LLVM, well, Clang is part of the LLVM project. It's a C and C++ compiler. There's Rust, Julia, which uses it as a JIT compiler. GHC also has a backend for LLVM, and there are many, many more. So let's jump right in and look at what the LLVM code looks like. So,
can you make the font a bit larger?
Sure.
Sure that the video is also.
Yeah. Better?
I think that's better.
Okay.
Also.
Too many key mappings. Is the light okay?
Trying as usual.
Okay.
Yes. Yeah.
Very good. Okay, great. So, just a few things about the syntax. Global variables are prefixed with an @ symbol, local variables with a percentage symbol. Everything is explicitly type annotated. We can define functions globally. This is going to be the return type, 32-bit integer. This is going to be the global name. Then we have 3 arguments, all of them 32-bit integers with names ABC, which are local to the scope of the function. Then this static single assignment form means that every name that we have in a block can only be assigned to once. So here we kind of make up a sort of temporary name, we call it 1, and we assign to it the multiplication of B and C, and then we assign to 2 the result of adding A to the multiplication of B and C, and then we return that from the function. And then we define a main function, which calls this function add mul on the parameters 1, 2, 3, and returns that result. And now we can generate assembly from that. And it's going to generate, well, machine assembly for this particular target. Or we can also directly execute this code, which is going to return the result 7. In this case, as the return code of the program. I'm showing this sort of to just make the LLVM language a bit more familiar what it looks like, because in the end we're going to see a lot of it as output of our own programming language that we compile. And of course, we always need to talk about the factorial function. And you can also write it in LLVM. One of the things I want to show with this is that in an LLVM function you have different blocks. All of these blocks get names as labels. Here we have an entry block which compares the parameter n to the value 0, and then we can do conditional jumps to these different blocks by their label. Here we jump to a label called base case, in the case that the condition is true, so in the case that n is equal 0. In the case that the condition is false, we jump to a label recurse. Then we can also unconditionally branch, which just means jump to the label return in this case. In the recurse block, we calculate n-1, we call the factorial function on that, we multiply n to the result, and then also jump to the return block. And now what's important about LLVM in the single static assignment form is that if we come from 2 or more different branches and we need to pick one value, we need to somehow have a way to pick a value depending on from where we came. And this is what these so-called fine nodes are for. So in the case that we come from the base case label, we're going to pick the value 1. In the case that we come from the recurse label, we're going to pick the value recurse factorial there. We'll assign that to result and return that from the function. So this is also to make you familiar with these fine nodes. It's a way of joining back together after some different branching happened. And we can also execute this right away. And we'll get the factorial of 5, which is 120. Okay. So what will we do today? We'll write a small simple functional language. It's going to be based on the simply typed lambda calculus. We'll have 2 base types, integers and booleans, and function types a and b for specific a and b. We'll have some literals and variables, if branches. We have primitive operations, addition, subtraction, multiplication, and equality comparison. And then we have lambda abstractions and function application, and non-recursive let bindings within expressions, and mutually recursive global bindings. And we'll have one main function. So a program in this made-up language might look like this. We define factorial here in a tail recursive form with an accumulator. Then we use it in a function that we call factorial with an initialized accumulator initialized to 1. And the main program just calls the factorial on a parameter n. This function also has support for higher order functions, so we might define a function apply, which itself takes a function from int to int and an int, and then just applies that function. We can have closures, so we can define make adder, which takes a variable a. We capture that in a partial application to addition, and then return the partially applied addition, so we return a function that expects another value to add to a. And we can also assign these to variables and call functions with these. So these are the things that our language will support. So what kind of compiler pipeline will we need for this? We'll need a parser. That one, I'm afraid, I did not implement. So we'll be working directly on the AST, which I think here is actually easier. Then we have a small type checker, which for this language is extremely simple. We convert it to another intermediate representation before we go to LLVM. I'll motivate that very soon. Then we convert to LLVM IR. If we want, we can ask the LLVM optimizer to give us better code. We generate native code, and then we execute it and see if it gives what we thought it should. So let's start with defining our abstract syntax tree as a data structure. We'll use just text to refer to variables. I should say I'm using protolud here simply because the code that I based this on by Stephen Deal also uses protolud. And just to mention, so more text, less string is essentially what we'll see of that here. Then we define types, as I said, integers, booleans, and this is a function type from A to B. Then we have our literals, integers and booleans. We have our primitive operations that I mentioned before. Arguments of functions are always explicitly type annotated, so we'll have them as a pair of a name and a type. And then the abstract syntax tree for expressions as literals, variables, let bindings, if expressions, function application, and function application always takes one function and one argument at a time, but lambdas can actually be defined with multiple arguments at a time. And then a program has global bindings. Such a global binding has a name, an argument list, a return type which is explicitly annotated, and then body. And the program is a list of global bindings and a main function which is just represented as the argument list and the body. And we say it always has to return integer because otherwise in this setting it's difficult to deal with the result. And because I didn't write a parser, I wrote a handful of smart constructors to make just the code a little bit more sane to read when I show small example programs in that. So let's look at an example program right away. Again, the factorial function. So we define a global binding factorial prime. That's the same code I showed in the slide before. So this is the tail recursive form of the factorial function. And then we define a global factorial. And then this is our main function, which calls the factorial on the integer value 5. And we have a small type checker. That one, in the interest of time, I'm not going to talk about, but it's in the code if you want to look at it. It's very, very simple. There is no inference going on anywhere. It's just checking that the types match up. Okay. So now why would I want to put another step in between and not go directly from there to LLVM intermediate representation? If we just compare the kinds of features the languages have, in LLVM everything is explicitly typed, so the AST is fully type annotated. Then LLVM distinguishes global and global variables explicitly everywhere. We don't do this, we just have variables. LLVM only allows global function definitions. We have lambdas, so this is kind of a big difference between the languages. LLVM, of course, also doesn't have any closures natively. That would be silly for an abstract assembly language, I guess. And also in LLVM, of course, all functions have to be fully applied, so there is no such thing as partial application. So it's a bit easier to go through an intermediate data structure than to try to handle the fully general LLVM AST right away. So let's talk about this intermediate representation. Maybe a side-by-side view is actually helpful for this. Okay, so the beginning is very similar. We have integer and Boolean types. Also name, we use the same type as in the surface language AST. However, we distinguish function types. Oh, I'm actually ahead of myself, sorry. Closures come later. Okay, so we have function types. Here the type already carries all the argument types right away. Instead, in the surface language, we have these pairs of A to B, and then a function of 2 arguments would be a function that returns a function, this kind of stuff, whereas here we have all the argument types right away. Literals and primitives are going to be the same as in the surface language. Arguments, same story. The abstract syntax tree distinguishes local and global variables. Let bindings and branches are the same. Primitive operations are fully applied. That's why we have a list of arguments. We only have binary operations, so it could actually also be a tuple, but anyway, it's a list here. And function calls are also always fully applied. And you see the AST is fully type annotated. Every node carries a type around. And then global definitions are the same as before. A name, argument list, return type, body, and the same for the program. A list of global bindings and the main function. So, how do we get from our surface language to the intermediate representation? There is a module for that. And so, such a transformation is going to need some sort of context to keep in mind what kinds of variables we have around. We distinguish global and local, so we have two such contexts, which are a mapping from name to type. So we have a global and a local context. Then we're going to need a counter for fresh variable names whenever we create something new. Like, for example, when we find a lambda in some expression, we're going to need to lift this out into a global function. We're going to need some unique name for this. And what I'm going to do here is I'm just going to count up an integer and attach that number to these names. And then we also want to write out a list of globals whenever we do this. So to represent what this kind of transformation from an simply AST to an intermediate representation AST is, I'm using the reader-writer state monad, where we read global and local context, we write a list of global bindings, and we have the state account for these fresh variable names. Then there is some bookkeeping stuff for generating such fresh names with a prefix and defining global functions. Transforming types for now, before we deal with closures, is very easy. We just map ints to ints and bools to bools. And then to transform an expression, literals are translated right away. There is no difference between them in those two languages. Variables, we check whether it's in global or in local scope, and we check its type, and depending on that we generate a local or global variable in our intermediate representation. Let bindings, essentially the same thing, just we need to also type annotate it, and when we compile or when we transform the body of a let binding, we need to add the name that was bound in this let binding to the context, to the local context. So this is what is happening here. The reader monad has this local function where you can locally change the value that is being read. That is what I'm doing there. Conditionals, the only difference is that we also need to type annotate it. Here I'm just picking the type of one of the branches. Primitive operations. If we encounter a naked primitive operation, applications will be dealt in the next step. If we encounter a primitive operation naked, then this means that it has not been applied to anything. So we just lift it out into a global function, which we call whatever it is, add, subtract, which expects two arguments and then performs that primitive operation. Function applications, as I mentioned before, in the surface language are always one argument at a time. To get to our intermediate representation, we need to have these arguments bundled up into one list of arguments. So we have a function here which takes this deeply nested tree of applications and flattens it out into a function and then a list of arguments. And then we check what kind of function it is that we encountered. If it's just a variable, then we turn this into a call of this variable. For that we have a helper function which is call. If the thing we are applying to is a primitive operation and we are applying two arguments, then we can directly turn this into a primitive operation. Our intermediate representation has them directly. And in any other case, we also call this helper function call, which will be more important later for the step when we have closures. So what this call does is it fetches out all the types transformed into the intermediate representation for the function itself, the arguments, the return type. It uses in particular the functions type to check if the function was fully applied or not. And in the moment we only support fully saturated calls, and if we're referring to a global variable, then we generate a call function for that global name. In the other case, we consider this an error and just panic out. Sorry. And then global bindings, we generate the type for this global binding, and we transform the body of the global binding. And for the transformation of the whole program, we first have to build up a scope, a global scope, because we said we have mutually recursive global bindings. So we build up the scope with the names and types of all the global bindings, and then iterate through all global bindings, transform them, and then go through the main function and transform that one as well. And this is very dry if I do it like that, so let's look at what happens to the example code I looked at before. So we had this factorial here, and now if we can just pretty print it out and make sure that it is the same thing, and now we can also type check it, but we can in this case assume that it is type correct and just pipe it directly through the transformation into the what happened? Okay. I think I somehow managed to freeze Tmux. Okay, so if we transform that example, oops, it looked like this before. So we have our definition of factorial prime that just becomes a function definition in the intermediate language. The only difference really is this application of the primitive operations. Here we have a primitive operation applied to an accumulator applied to a variable, and this turns into a primitive operation directly with two arguments unfolded. Call function, the same thing, we have the full argument list right away. Everything is type annotated, so it's a bit more bulky to read. And yeah, that's all the differences. So functions are fully applied. Argument lists are stashed together into one list. Now, how do we go from there over to LLVM?
Before you go there,
yeah.
Question. Could it be that the means on how you do name allocation will make it such that you can actually have clashes? Because you're not renaming any of the global names. Which means if you have a global name like global name 0,
yeah.
and if a local name which you want to generate that has the same one,
yeah.
then you're going to clash on the global names.
So the counter is the same for global names and local names.
But you're not applying them, or do you?
So this...
Just because factorial prime wasn't renamed to...
Oh, in this sense, okay. So global bindings that were global bindings in the original surface language are going to be mapped under the same name, and they are never going to be duplicated. right? So if the name was unique in the surface language for a global binding, it's still going to be unique in a global binding in the intermediate representation.
So I understood that in some cases we need to lift local functions to global functions.
They just get a unique name every time we do this with the counter in the end.
And how do you make sure? But that name lives in the same namespace as the old global functions, doesn't it?
Yes, that's right.
So it could be a clash, because you're not avoiding the old global functions when allocating new names.
If you have an original function called like global 0 or something.
So they are named things like underscore underscore lambda 0 or underscore underscore
that
lambda.
Would be a valid global name, wouldn't it?
Ah, yes, okay, I got it. Yes, so for simplicity's sake, we're saying double underscore as a prefix is illegal.
Yeah, that's fine. Just to be aware of these.
Yes, of course.
Nice.
Now I understood the remark, yes.
Easy fix would be that you just rename all names.
Yes,
that's
sure.
what GC does.
Or you just give an error message with like my brain just exploded. It's also generally accepted.
If you rename all names, then maybe if you're linking to something else, you can't find the names anymore.
Oh yeah.
Yes. In this case, we're going to make it simple. We're going to have only one main function that is globally visible and for external linkage. Everything else is going to be an internal function, which also has the benefit that the optimizer can just scrap it away if we don't need it. Yeah. Okay. So, if there are no further questions about that so far, then let's have a look at how we actually do LLVM from Haskell. So there is this LLVM general library. It has two parts, a purely Haskell part in which you construct an LLVM AST as a Haskell data structure, and then an impure part which is bound to the C++ LLVM libraries and keeps the AST as a data structure in that realm. So the kinds of things we have from that module is, for example, we can define a type with a certain bit width, here a 32-bit integer, or we can create a global definition. It has a few default values for particular kinds of global definitions, such as function definitions. We give it a name, we give it an argument list, a return type. Then expressions happen in blocks, and a function can have multiple blocks. Those were those things that we saw before, named entry or base case. Here we're going to have just one called entry. Then in there we can have expressions which give a result that is given to that is assigned to one of those local names, such as %1, %2 that we used before, or we can also use a written out name like %condition or something like this. And this binding distinguishes them as name if you want to give it a string name, or unnamed if you just want to give it a number as a name. And then this would be an addition between A and B, and then blocks can have a terminator, a so-called terminator, and returning is one of those. And here we return a local reference result, which is the result of adding A and B. And then the module consists of global definitions, here just of this one that we just wrote. And then we need to, at some point, invoke the non-pure bindings to the C++ LLVM library. And for that, the bindings use continuation passing style, because they need to always keep some allocation somewhere around in the C++ world. So in the beginning it needs to allocate some context in which LLVM keeps some bookkeeping information, and then we generate a module in the C++ bindings, or in the C++ side. And for that you will see a lot of this continuation passing style where we say with context, with this thing, do that. So what does this do? Let's see. to LLVM module. So this now indeed generates such a module, global definition add, and here are these expressions. Okay, now keeping all these data structures around manually when writing our translation stages could become a little bit of a hassle, and thankfully that is going to be now the bit of code that we'll use from Stephen Deal. He wrote a quite nice layer in between where we keep around a state monad for an AST module. So this is going to be the module of LLVM where we have multiple global definitions and we can add to them and read them out. We can add new global definitions, which is going to be for a function definition. We distinguish between such definitions that are externally visible, used for the main function, and internally visible, only used for local functions. And we can also do external declarations for functions that are not defined within the same module, such as, for example, malloc, if we want to allocate heap memory. It has a few handy, easier to type definitions. Also a way to generate unique names which it needs internally. And then for the level of expressions within a function body, so when we build up these blocks out of which a function, for example, consists, we have another state which we call code generator state, which keeps around these blocks that we need to build up a function body. Each block consists of a list of instructions and then possibly a terminator. The end of a function always needs a terminator, but blocks in between don't have to have one. Let's see. It has a symbol table which we can use to use our own notion of variables in combination with these bindings that appear in LLVM. So in our language we're going to have something like let a equal 5 and then we're going to translate the 5 just to a literal 5. But the a we're going to put into a symbol table, and when we look that up we get out directly the LLVM operand that we had bound this to in our surface language. We're not going to actually put the name a into the LLVM code. And then we can refer to local variables, global references such as functions when we want to call them. We have primitive operations as well, such as addition and multiplication. These are handy shortcuts for adding a new instruction into the current block, which is going to be whatever operation is defined there. Then we can also call functions. I'm going to use a difference between the C calling convention for calling functions like malloc, and all the functions that we have internally are going to use fast calling convention that LLVM offers, which is going to be trying to do things a bit faster, passing everything through registers if it can, this kind of stuff. Single assignment form in LLVM uses an infinite set of registers, but sometimes we actually do need something allocated on the stack. For this we have alloc A here, which allocates space on the stack. And then we have branching, conditional branching, and the phi node that we talked about before. So let's look at what happens, or how to use this now to transform our intermediate representation into LLVM. We're going to assume that if a program was type correct, it is going to compile to LLVM. Everything else is considered an error. So to keep this a bit more simple, I won't be dealing with eithers or any such thing, but just panic if there is an issue. Types translate fairly straightforwardly, integers and bools. Functions, LLVM has its own notion of function types, and the intermediate representation we define already has the full argument list unpacked into its type, so we can just directly translate that into LLVM. Expressions Literals are straightforward. For local variables, we just use this CodeGen module's notion of a symbol table and look up the name in that symbol table and get out the corresponding LLVM operand, which is then going to be something like a %5 or something, such a name. Global variables we refer to with the LLVM notion of global variables. Let bindings will assign to the name in this CodeGen symbol table the result of translating the expression that we bound in the let binding, and then afterwards just generate the body of the let binding. Conditionals are a bit more interesting. There we need different blocks and we need to branch between them conditionally, and then in the end we need to join the control flow back together. So we have a then, an else, and an exit branch, a block, and also an entry block in the function. In the entry we just translate the condition into LLVM, and then if the result is true, we jump to the then block, otherwise we jump to the else block. This is very similar to what I showed before in this LLVM IR factorial function. And in the end of those two blocks we have this phi node again, which depending on which branch we came from picks the corresponding result. Primitive operations can be translated directly if they're fully applied, and at this stage they're always going to be fully applied. That is what the previous transformation will make sure. And function calls call out to functions in LLVM directly. Okay, then generating a global is adding an internal function definition with the name of that global and then translating its body into it. And for generating the whole program, we generate all global bindings, and then the main function, we call it __ main, in the same notion that any name starting with 2 underscores is illegal for the user to use. And we also make malloc available because we're going to use it later. Okay, so let's see what actually happens now if we apply all this to our example code. So here we have transformed to the intermediate representation, and now we're going to transform that to LLVM. Let's see. And you see this looks very nice and very readable. I did actually, let's see, I did actually add a pretty printing capability to this. Let's see. There we go. But I don't think this really helps.
How do you pretty print?
So I just generated 100 orphan instances for some generic pretty printing library for all the LLVM AST data structures.
Oh, I see. Yeah, it looks like is that you're using too much. Your indenting is sensitive to the name width.
Yes. So yeah, I didn't look into the parameters of that pretty printing library much. For most manageable expressions, it looks fairly readable. At this scope, it kind of just gives up.
But you could render this to the LLVM output, couldn't you?
Exactly, and this is what we're going to do now. So let's see, print LLVM, and the types don't match because this is still pure. Yes. Okay. So now this is actually the LLVM that we generated out of our factorial program. So we have the global definition factorial prime. It's marked as private because we define our own local functions as internal. It takes two parameters, accumulator and n. And it does the comparison. So this is the if branching that we just talked about. It has the then branch and the else branch, where it does the call with the recursion. So we let's see. We multiply the accumulator by n and then subtract n, subtract 1 from n, and we call recursively on those. Then in the exit block, depending on which branch we came from, we either return the accumulator right away, so that's the base case, or we return the result of this recursive call, and then we return from the function directly. Factorial is just a wrapper that applies 1 for the accumulator, and the main function calls the factorial on 5. And now let's see if this actually gives the right result. It does, 120.
So this so far is not actually using the LLVM library yet before you executed it, the printed file. It was still using the pure LLVM general stuff?
So everything up to the very large looking data structure that we saw that the pretty printer couldn't really handle anymore, that was all the pure bindings.
Right.
Now to get this version you actually do need to use the C++ LLVM library.
You mean to execute or?
Also to print the nice version this year.
I see. So the printing part is not part of the general pure?
That's not part of the general pure, yes. And this is actually, it can be a little bit of an issue when you have a bug in your compiler and you try to debug it, because if you have LLVM not compiled with debug flags, then it's just going to segfault. And if you have it compiled with debug flags, it's going to assert, which is also not very nice to debug from GHCI. So in my translation here, you'll actually see a few assert functions in Haskell, which is just because Haskell is easier to debug than assertions in C++.
Okay, so basically what's happening is that you're transforming into the pure representation, the Haskell data types that LLVM general pure provides, and then you call the LLVM general with the bindings to actually generate LLVM through the C++ kind of layer.
Yes.
And then you print it.
Yes, exactly. That's what's happening there. I can show you the code that does this. So there are a bunch of functions that you can use. So with module from AST means AST is the Haskell data structure which represents the LLVM AST, and then this function turns it into the C++ version of that. And you can also get access to the assembly for the target machine, for the native code. And for executing it, there is something called an execution engine, which comes with a JIT, which can take LLVM code, turn it into native code, and call it right away. And then I'm using libffi, foreign function interface, to call that on a number of 32-bit integers. Now, I actually forgot to say before, and it's never mentioned in the type checker, but the main function currently should only take integer arguments. Anything else is probably going to do with something very strange. But yeah, that's what we're doing here. So from the Haskell side, we accept a list of integers. I'm currently not checking that the argument list and the main function from the code that we wrote actually match. So if you give something wrong, it's going to read something out of the registers. So yeah, there is room for improvement. That's for sure.
One more question.
Yep.
So the LLVM general pure, what kind of option do I have to dump it into some representation? There is no way to dump it into the textual IR, as you mentioned. What about the bitcode?
That I actually didn't look into myself, I'm afraid. But yeah. I mean, I would suspect that if the C++ library can do it, then it probably has a binding for it. But by itself...
Yeah, I mean, once you go to the library, then probably, yeah.
Yeah.
I was kind of more thinking of on the side before I need to use the
Right,
C++
right.
part.
Yeah. That I don't know, if you can go to the bytecode there, or bitcode. Okay, now one thing that I promised before is that LLVM can also do optimizations. So now let's see what it does with this factorial function if we apply some optimizations to this. For that I have a function called print LLVM opt. In LLVM you can build up these optimizer pipelines or sequences. You can actually use, or you can have a lot of control over this yourself if you want, which if you were serious about writing a very good compiler for some very good language, you would probably want to do. Here I'm just using one of the prearranged settings, which is the same as you would get for Clang-03 or something like this. And there are a few different ways you can do this. One, which I call no inline, is just setting up O3 small optimization level to 1, and it can in principle do something like vectorization optimizations or simplify lib calls or syslib calls or something like this. And if we apply this, we will actually see that most of our calls have been annotated as tail calls. That's already quite nice. And if we look into the factorial prime, we actually see that there is no more function call to be seen anywhere. So it has unrolled the recursive function call and turned this into a loop, which the native architecture is going to like much more. And now we can ask what happens if we allow it to inline functions. And this I find quite impressive. It just says the factorial of 5 is 120. Why would you bother calculating it anymore? Okay, now you could say I might have been cheating because I wrote it in tail recursive form, so I did half the job for the compiler already. So let's see what happens if we don't. Ah, what's happening? Why is it putting me into insert mode when I'm going there? This is very strange. Okay, something is definitely... I recently did an update of some of my Vim plugins, and that might have been a bad idea.
Is it shift?
Is it shift that is... No, caps lock is not set up, no. Let's see. We can just open the file directly, that is going to work. And we'll, okay. So there we have another version of the factorial. Oh, first of all, okay, what is going on? Okay, I see. First of all, we had before passed the value 5 already to the factorial function. If we don't do that, but we still give it a parameter, then the optimizer will actually do all the inlining and loop unrolling, but it cannot calculate 120 yet because there is no 5 for it. And then we can check that this code still gives the right result. So we can play around with our native code and make it execute. Okay. Now another version which is not written in a tail call, in a tail recursive version. So here the factorial just takes one argument n, and then we compare, we return 1 in the base case, and otherwise we first do the recursion and then multiply by n. So let's see what happens there. And in this case, it still says 120. So it actually, even though we did not write it in a tail recursive form, was able to unroll everything and inline everything and give the result right away. And if we leave an argument open, so this is now a version which is not tail recursive, but still takes an external argument, then we will get just one main function, which also has no function calls in it, but just a loop which calculates the factorial for us. And it still produces the right result.
Interesting.
So basically you optimize it to the previous version, and then the previous version we can always see that.
Yes, yes. So it kind of quite some stuff.
What would happen if you would go for the Fibonacci function and write it in this dumb version? You have two calls, two recursive calls. Would it realize that actually these are pure and thereby the results could be memorized and shared and to have unique bounded memory?
So I played around with that a little bit, and the best I saw it do was to unroll one of those function calls, but not the best. So, and later on I will show an example where we go fully crazy and yeah, it does not do magic, but it can do quite some impressive stuff. Yeah. And also an interesting feature, we can, on top of that, optimize with target-specific optimizations. And if we generate the LLVM IR for this, you see that this becomes humongously huge. And the reason for that is that it actually detects that the processor has some vectorization, some SIMD instructions. And I have not done any benchmarking. The code is currently not set up for that to make sense, but who knows, maybe this is actually better. And you can also then print the native assembly for that, and you will find that indeed there are some SIMD instructions showing up.
Did you look at the code? So what's the trick it's doing?
No, I didn't dig through it to see what it exactly does. But I would assume that it maybe just loop unrolls 4 steps or something like this, and then vectorizes those. But I haven't looked into that. I don't know.
It seems the only thing you can do with.
Maybe more than 4 steps, I don't know, but yeah.
Or could we have a quick look? Because that you should just see, shouldn't you?
So let's see, this is the LLVM.
UNR unrolled 19, 20, is that one?
Yeah, it looks unrolled. I mean,
Yeah.
And then the vectorization is, I mean, how is it used then? If you unroll, I mean, it's just,
oh yeah.
I mean, what do you vectorize?
Data dependency, yeah. It's kind of
So it does 4 integer 32 multiplications at a time, right?
Yes. I have not gone through the details to see how this makes sense for the factorial function. But
Okay.
yeah. I think it's interesting to see that the capability is there, and in practice one would have to see if for the particular use case it makes sense, because I mean you also of course blow up the code size by quite a lot.
Yeah.
So it probably depends on the particular use case. I was also not at all careful in configuring the optimization stages with the parameters. So I mean, I just turned every knob to 11 and see what happens. Okay. So now that we've seen that, let's talk about closures, because so far we've only had functions on the global scale and fully applied all the time. So how would we actually go about getting closures into our language? There are many different ways to do this. I'm going to take a fairly simple way. So a closure, when we need to generate it, might capture some variables from the local scope. So the partial application of A+, for example, before needs to capture the value of A. And then, because LLVM later on only has global functions, we need to define out of that a global function which takes the capture and the remaining arguments and then produces a result out of that. So to give an idea of what that should look like, I wrote a simple version of that in C. And the idea is essentially that a closure is a struct which has a function pointer and an environment pointer. The calling convention that we're going to use for that is going to be the first argument is a pointer to the environment, and then the rest are going to be the remaining arguments, so this depends on the particular closure's type. What's important is that the type of the environment doesn't show up in this, because in the end we want to be able to pass this as a value to to a higher order function which just expects as an argument a function from int to int. And if the type of the environment shows up in that, then we have a problem if we have an environment that binds two variables instead of just one. So we need to get rid of that. Then the environment itself is just a struct holding all the values that we bound. Then this is going to be the global function that calls our closure. So it takes the environment pointer and the remaining arguments, and it extracts the bound variable out of that argument and then returns the result of adding a plus b. So it then performs the remainder of the operation, the operation that was left to do in the closure. And then to build up such a closure, here we have this makeAddr function again. We allocate some space. We're going to be bad and not care about freeing it again. So I'm sorry, I did not implement the garbage collector, I'm afraid. So we'll just do a bunch of heap allocations and they will pile up and we'll leave happily.
I'm calling the police. The film police.
Then we access what was bound in this environment and we call, and then we build up this closure structure which has the function pointer, which is the function that is going to execute the action, and then the pointer to the environment. And we just return this struct, and this is now the value, the closure, that we can pass around. And then our function from before, apply, which expects a closure and a value that it can apply it to, just unpacks the function pointer and calls it on the environment pointer and the argument. So this is going to be how we represent all our closures. And for that we will extend the IR. Are we on time, by the way? Doing fine, good. Oops. Okay, I'm very puzzled, but I seem to have... some reason. Okay. Let's see. So now I need to go to the version which has closures. And there we add two new entries to our AST. One of them to create a closure. That is the part where we refer to a global function which is in the end going to execute that closure, and the environment that we're going to bind, which is just a list of expressions. So this is the stuff we capture. And then we also need to call in a closure where we take an expression, which is the closure itself, and then an argument list, which are the remaining arguments to apply that closure to. We also distinguish them from functions in their type. And to keep things simple, we're going to have functions only for globally defined functions that were globally defined in the original language, and closures for everything else that shows up anywhere, like lambdas that we define locally, partially applied functions or operations or something like this. And also every function that expects a function as an argument is going to expect a closure. Otherwise we would get into trouble that if it expects a global function, which is a function pointer, which could not have an environment, and we try to pass a closure to it, it wouldn't work, so everything becomes a closure. And we also changed the global definitions type. We allowed to define these closure functions globally, which then actually execute with the environment. So they have a name, they have environment capture, and they have an argument list. They have a return type and a body. The rest is unchanged in the IR. What we need to change now is how we transform over. Let's see. Yes, so we have a function which can define a closure globally, and then we have a helper function which is called lift closure. And most of or a lot of the work that is necessary is going to happen here. So what we do here is we take an expression and we look for all free variables in it. We take only the local free variables in it. And this is going to define our capture or closure environment that we need to capture. And then we define global closure, which expects that environment and the remaining arguments, and return a closure value, which is make a closure with that particular capture list. Transforming the type, we add one more case where every function type is going to be transformed into a closure. This is what we're going to use in the end for global functions or lambdas or whatever that expect functions are going to expect closures in our IR. And then, because our surface language has this feature that both global functions and lambdas can be given an argument list, it could happen that this argument list is empty, and then the type system in the surface language cannot distinguish an integer value from an integer producing function that doesn't take any arguments. So for this I kind of implemented some implicit type conversions. So promote type takes two different types and turns them into the compatible common type, which for most cases doesn't do anything. And if you have a function without arguments and its return type, then it turns it into the return type.
Couldn't you have switched to just taking a non-empty list there?
That would also have been an option, yes.
So I think the distinction only comes across when you really need a unit call.
Yes. Yes.
So
for some of when I was playing around with this, sometimes it was useful to have like global constants, but I didn't want global constants, but I didn't want to define global constants as a feature, because then you also need to talk about initializing them in LLVM. And then if you have a function without arguments, that's essentially the same thing.
I see.
So yeah, that was sort of the motivation for it. Then this promote function just does the same thing on the value level. So before we were talking about the type, finding a common type. Now we take two values which might have different but compatible types, and then we convert them into their common type. And the conversion checks, is it a function or closure without any arguments? If so, just call it without arguments, and otherwise just pass it through. And now we can do a few more things in this apply stage, where it might happen that we have not fully applied functions, or that we have not fully applied primitive operations. So for example, if we have a primitive operation with applied to just one argument, such as here, then we lift that into a closure which expects one extra argument and then applies the captured value and the extra argument to the primitive operation. So if we have something as we had in the example code, plus applied to A, which is a partial application, then this is going to turn that into a closure which captures A and then expects B as an argument and returns A plus B. That is what is happening here.
if you have multiple of these partial applications that are of the same form, will you generate a closure for each of them?
Yes.
But one could share them in principle. Because they have the same structure, so...
Yes. So there is definitely room for optimizing and improving. Currently, this is extremely wasteful with global definitions. Also, if it just encounters a naked primitive without any arguments, for every single one of them, it's going to generate a new global binding at the moment. So I don't keep a list of things that have already bound. Mm-hmm. A simple solution there would be, since we have a finite set of primitive operations and a finite set of possible partial applications, we could just define all of those up front and then use the corresponding name, like add with one argument or something like this. But yeah, to keep it simple.
Yeah, no, I'm not criticizing. I'm really just trying to understand how much is done and how much is not done.
So this is, if you wanted to write an actual real-world compiler, you would probably want to deal with this a little bit differently. But currently we're just throwing global definitions out wherever we can. Yes, then calling a lambda is also just using this helper function call, which is then in charge of dealing with all the complexity of actually performing a call. If we encounter a lambda, this case was not covered before we had closures. If we encounter a lambda in an expression, then we also lift that one out as a closure. It could potentially have variables bound in its body. It could be that it could also be lifted to a global function, to just a function, but we do not check for this case. We just make a closure out of it every time. Okay, so now this call function considers the fully saturated call, but also over and under saturated calls. So if we call a function with too many arguments, that means that it is a function that takes a certain number of arguments and then returns a function itself. So the way we're going to deal with this is we're going to turn this first into a call with the right number of arguments, keeping the other arguments in mind, then taking the result of that first call and just applying that again to the remaining arguments. So this way we kind of recurse through a potentially large tree of oversaturated applications. And partial applications, there we have a special handler for that. It could actually just go up in there, but anyway. So if we encounter a partial call, then we need to make up names for the missing arguments. We use the same scheme as before, underscore, underscore, and then argument and a number. And then we generate a closure which captures whatever was in that call expression, and then performs a call of the function with the arguments that were already there in the beginning, which are now captured in the closure, and then adds to that argument list the missing arguments for which we now just invented names. Okay, so let's look at this in practice. It's very puzzling. Okay. So this example that we saw on the slides before, higher order, it defines this function apply, which takes a function and an argument for that function, and it constructs a closure out of a partial application to the add primitive, and then uses those. So if we transform that now to...
You have to reload.
Oh, I have to reload, right. Thank you. Yes. Okay. So what this does now is it defines a closure. So this is the naming scheme that all these global bindings that we invent are given. Closure and then a counter. It has a capture of one argument, A. So it captures the value of A. And it takes an argument B, and then adds A and B with the primitive add operation. Apply expects a closure as an argument and a value x, which is an integer, and then calls that closure on the argument x. Make adder takes an argument A, returns a closure, and here this make closure expression refers to the name of that closure function here, and the capturing the argument or the value of A. And then the main function takes the argument n, assigns the call of make adder to add 3, and then calls apply on add 3 and the literal value 4. So let's see what happens if we turn that into LLVM, and let's print it right away. Oops. This thing used to be impure, and I'm not used to that yet. Okay, so this is the LLVM IR to the our IR that I just showed you. We have this global definition here. It takes the environment pointer. Other than C, LLVM doesn't actually have void pointers, or it doesn't call them like that anyway. So what we use is just a byte pointer, just points to an 8-bit integer. That's it. Bitcast is an operation which casts from one type to another. So here we cast that byte pointer to a pointer to a struct of one 32-bit integer. Get element pointer is an instruction that does pointer arithmetic in LLVM. So if you have a pointer that could mean that you actually want to use it as an array, right? It could be the pointer to the first element, and then it could have a certain number of elements, and these elements themselves might be arrays or structs or whatever. So you might want to do some indexing of multiple stages. So get element pointer takes the pointer with which you want to do your pointer arithmetic. Then the first argument, the first index, is this array index. So if we just have one thing that the pointer is pointing to, this is always going to be 0. And then this is the index into the struct itself. So this means take the first of the potential array and then the first element in that struct, which is this 32-bit integer. So this is our A that we captured. Now that we have this pointer, oh sorry, I slipped the line, I was here before. We load from that address, that is what this load instruction does, and then we add the result of that load to the argument that was missing, B, and return the result. So this is the partial application of add applied to one more, the missing argument B. Then the function apply takes this closure, and you can see we represent a closure as a struct which has a function pointer here. So this is the syntax for a function pointer returning a 32-bit int, taking a byte pointer and an integer, and the star here means that this is a function pointer. And then we take the byte pointer itself in the struct, which is the pointer to the environment, and this represents the closure as a whole. And then here is the value x, the extra argument. We extract the function pointer out of this struct, we extract the environment pointer out of this struct, and we just call the function pointer on the environment pointer and the argument. So this is going to call closure 0 on the environment pointer and on the value x. Okay?
So coming back to Simon's question, right?
Mm-hmm.
Seems like LLVM should be able to optimize a bunch of those, duplicate closure.
Yes.
Right? I mean, it seems like this shouldn't be difficult. You already lowered basically and threw away the different type names. It's all just byte pointers and stuff. So
yes,
you should be able to figure out that some of the blocks or functions are identical.
Yeah, and I mean, we haven't applied any optimizations yet. We'll actually see that it does quite a lot. Yes, then this make adder here, we use malloc to allocate space. This crazy get element pointer expression here is size of. If you Google size of LLVM, you find that this is the recommended way of doing things. So LLVM does actually not have a size of operator, surprisingly. So if you calculate the pointer to the second element in an array, starting from a null pointer, what you end up getting is the size of one element of that array. So this is a size of in LLVM. I think there is also some ways to do this differently, but then you need more complicated features of the LLVM library where it needs target-specific information about how it would do alignment and all sorts of stuff. So this is the easiest way to do it in LLVM IR right away. Then we need to cast this to our environment pointer. We fetch the pointer to the first element. We store the value that we want to capture into that environment so that it now lives on heap. We build together our closure struct. So this is also kind of in the code that we generate. It's a number of instructions, but when printing it out, it already condenses it together to one joint instruction. So what this does is insert value, inserts a value into a certain position of a struct, and due to this single static assignment form, you cannot have one struct and then assign the first and then the second and then the third element, but every time you do this, you need to get a new struct which has one more thing inserted. And the way to do this is to build one with the first field already inserted, because that can be done in one instruction, and the rest is undef for undefined. And then we insert into that so far undefined the value that we want to put in there. So this is going to create a struct with two elements, the function pointer and the environment pointer. And then we just return this. And the main function calls makeAdder, calls apply on the result of makeAdder and the number 4, and returns the result. Okay, so now first let's execute this to see if it actually does what we think it should, and it does. 4 plus 3 is 7. And now let's see what the optimizer can do with this. Oops. LLVM opt. There we go. If we do not inline, then we see that a lot of this has been turned into tail calls, but otherwise it didn't actually do much, because it can't. But if we allow LLVM to inline all this, then very nicely it tells us that 4 plus 3 is 7, and even got rid of the malloc, even though we never freed, so it's actually wrong transformation.
Yeah, that's interesting. I mean, how does it know that malloc doesn't have a side effect which we want to keep? Is that declared somewhere?
Yes, so LLVM, I didn't need to do this myself, but LLVM has a list of functions that it knows about, and it knows about malloc and what it does, and some of the optimization stages in it know that, or are written in such a way that they can elide mallocs.
To put stuff on the stack instead of the heap, for example.
Mm-hmm.
I see. And how does it know that this symbol malloc is the malloc C implementation?
That's a good question. I don't know what would have happened. So currently malloc is defined as an external, right? So it knows that it's not defined in this module.
Yeah, I just wonder whether it's really just by name. So if you would call it our malloc, then it wouldn't jump over it, or?
That might well be.
You can probably tweak it in the options somewhere.
So you can definitely change the list of function it knows. There are bindings for that to modify that list of special functions.
Yeah.
Yeah, that's definitely the case. Okay. Now this is the same thing, but taking an external argument. And there it condenses it down to n plus 3. So even if it doesn't have all the constants available, it can still elide the malloc and everything and just say n plus 3 is the answer you're looking for. And it works. So yes, now comes the question, how much can this thing actually do, right? How crazy can we go? So let's write the factorial function with the fixed point combinator and see what happens. We actually have a strict language here at hand, so if we do this, we need to kind of build up our own thumbs, otherwise we have an infinite loop. So this is what is going on here. It's a simply typed lambda calculus, so we need to explicitly type every fixed point combinator. Here it's for a 2-argument integer, integer to integer. Here is where we kind of build up our sort of thunk. And then we do the magical recursive step where f is applied to itself. Here is the function factorial defined in open recursive form, so it expects as a first argument itself, then the accumulator and n, and does the factorial, and then we return the fixed point combinator applied to factorial, and we also initialize the accumulator as 1. And then the main program just calls the factorial on the parameter n. So let's see what this generates in unoptimized LLVM. You can see it's a bit. I won't go through it in all detail, but you see, I mean, we are really not saving up on global names. We're pushing out one closure after the other. The types become totally unreadable. And yeah, down here, the main function is then actually calling everything. And yeah, now let's see how much it can do.
Is this now for a free argument, or is this the fixed one again?
This is a free argument. This is a free argument, yes. And yeah, this is too much. Through layers and layers and layers of closure calls, it can actually not poke through, and yeah, so no magic. But still very impressive, I think, what it did before. And just to kind of convince you that this actually is a factorial, it does, no matter how convoluted, still work and produce the right results. Yeah, there is, I haven't looked in any way into this in detail, but I not long ago saw a talk where they were talking about implementing coroutines in C++ with Clang. And they actually put all the logic for the coroutines, so the allocating of the stack state that you keep around and everything, they implemented all this in LLVM directly with LLVM. You can kind of define build special functions in LLVM, which are taken into special considerations. You can use this, for example, for garbage collecting, to notify that special garbage collecting things are happening now, this kind of stuff. And they hooked into that in LLVM for managing their coroutines, and then aligned and designed the optimization passes in such a way, and added also their own optimization passes, that it can actually, in the cases that they presented anyway, fully elide out all those coroutines. So in the end, it becomes it turns into a for loop directly without any coroutine calls. So I don't know. I would be wondering if one could apply this kind of idea also to a functional language, maybe with laziness, and then this way try to elide funcs in places. I don't know. Maybe that would be something that one could do. Okay, anyway, we went through everything I wanted to show you. If you are looking for some ideas what you can do with playing around with this, there are a bunch of links I have in here, so you can try to get garbage collection in there, or make the type system polymorphic, play around with dependent types, these kinds of things. Otherwise, I thank you for your attention, and there are some references that are used in preparing this stuff. And if you have any questions, ask, and I'll be around still. So, any questions? Any crazy code you want me to type in? Any such stuff? It's also on GitHub, yes?
Again, a simple one, maybe it's one you asked previously. You're generating labels for if-else branches and the blocks.
Yes.
Do they also get unique names? So if you have multiple if-elses in a single function?
Yes, so this code is actually part of that module that I borrowed. And I think it has, it has its own notion of creating fresh names, and I think what it does is it takes a prefix and then it looks, has this prefix been used? If not, it uses that name directly. Otherwise, it attaches a number that counts up. So I think that would be what would happen with those labels, but I haven't actually checked. Yeah.
Cool. All right.
Okay. So yeah, the code is online. Currently only set up to work with Nix shell, but if you have LLVM 3.5 on your system, I guess Cabal itself or Stack should be able to deal with it fairly easily. Yeah, and if anyone wants to commit a Stack file, that would be very welcome.